Alright, so today, or at least this video, we're going to be talking about tests of independent samples. Now, independent samples, in this particular case, we're going to consider the time where we have two groups or two independent samples. So we're going to just, put a little bit extra stuff there, but there are ways beyond what I'm going over in this particular YouTube video of testing independent samples of more than two groups. We just use the term ANOVA to deal with those, and it's a little bit beyond the scope of this particular video because here we're just dealing with the two groups version. So whenever we're dealing with tests of independent samples, you do have to absolutely make sure that the people inside of both of your groups, maybe you have a treatment group and a control group, they're completely different people in these groups. You can't have somebody from your control group walk over and start participating in your treatment group, and you can't have the same for somebody who's in your treatment group walking over into your control group, because suddenly what you end up with is we've got 5 people maybe in our treatment group and 5 people in our control group, and if person 4 happens to be the same person, now we have some sort of dependency between these two groups. But if we don't have that dependency, where we have all of the different people in all of the different groups, we can say that we have independent samples. So one of the things that we really need to do ahead of time is check. Maybe you have a research question that you've been given during an assignment, or maybe you're trying to develop some sort of project yourself, but you have to check if your groups are independent. Cool. So that's one of the first things that you really want to consider whenever you're doing some sort of independent samples test. There are a bunch of different types depending on whether you have population or sample information. I think that I'm just going to go over the sample information one because we rarely have population information. So I'm going to go over this in the same format as the null hypothesis significance testing format. I did cover this in a different video that is like 2 hours long if you want to listen to it on fast forward. But when it came to that null hypothesis significant testing stuff, there were a few different sections that we could split this into. Some of it that you do before you actually go and, collect some data, and some of it that you calculate afterwards. So what are some of the steps? Well, step 1, or step A, according to my last video, we had to specify the parent population. And in this case, we actually have 2 parent populations because we have 2 groups that we're eventually going to collect data on. And because we are dealing with independent groups, both of those populations are considered independent, so we need to specify them both. Independent groups. So if we have 2 independent groups, then we have 2 populations that we need to, tell people about. And what's a population that I'm going to use? I'm just going to call these treatment and control for my populations. I might throw in different terms later on, like when I'm actually coming up with an example, but for simplicity's sake, we're going to call our control group, what are we going to call them? Yeah, we're just going to have it in green. We're going to call them X control. And my treatment group, or my treatment population, I'm going to call X treatment. It is in red. Again, if anybody's colorblind and can't see the difference, please let me know. How do we write this out? Well, the way that we try to write out our parent populations is we try to tell people as much about these parent populations as normal, as we can. That could mean, how does it distribute? How, do we know what the mean is? Do we know what the variance is? And depending on any other pieces of information you have, just try to figure out, okay, how do I communicate what these parent populations look like? Simplest way to do that is to, let's start with our control group. So X control literally just means control scores. So X control scores, squiggly thing means distribute, and we're going to say that in the population, the scores on whatever our control group is on the dependent measure, they're going to distribute normally, and maybe they're going to have some particular mean, and they're going to have some particular variance. Oops, that's the mean. Variance. Cool. I don't actually know what the mean is for my control group, and I don't actually know what the variance is for my control group. All I know, maybe I actually assume things. So there are these lovely things called assumptions that I also talked about in the other video. Basically, they're a possibly falsifiable claim about your data that you are making a statement about. And so if I don't actually know what the distribution or what the population of control looks like, maybe I'll just make an assumption that it's normally distributed. That assumption could be wrong if I never end up collecting enough data or looking at my data to check, but it's an assumption that I have to make in order to continue on. There are ways to check these assumptions later on, fortunately. So what does this say here? Well, I said that my control scores distribute normally around a mean with a variance. With a variance. Cool, so what do I have to do for my treatment group? Well, I have to do the same thing. I'm going to say that the scores on my treatment group distribute also normally with a population mean that I don't know what it is, and a variance that I also don't know what it is. And I'm just going to shorten treatment to treat because I'm lazy. But this says the same thing. This says now that treatment scores distribute normally around a mean with a variance. Whenever we're trying to describe populations, we tend to fall back on those descriptive statistics. Typically, the descriptive statistics that we're going to use in this kind of independent samples design are things like the mean, the variance. We're going to have some measure of skew and kurtosis. And the skew and kurtosis, well, if you look at what a normal distribution looks like, it's what we consider normally distributed, or it's what we consider to have no kurtosis and no skewness. So when we say normally distributed, people generally get a sense of what that means in their head. For reference, what is normally distributed? Well, here we're going to pretend this is a nice, lovely, normally distributed thing. Let me just get rid of some of the extra stuff. A normally distributed piece of data or bunch of data would look like this, where we have a good amount of the scores clustered in around average, but we haven't managed to make it like leptokurtic where all of the scores are bunched up around average, and we also haven't made it so that none of the scores are bunched up around the average like in a platykurtic distribution. And so with the normal distribution, if you're talking about kurtosis, you just want to have a nice, reasonable frequency for the scores that are clustered in around the mean, and less frequent, but not like a ton and not none, in terms of the scores that are spread out further away from the mean. We also want to talk about skewness when we're dealing with normal distributions. And what is skewness? Well, in terms of skewness, it means that a normal distribution does not have outliers in either direction that are really pulling the shape of your distribution off. Alternatively, the real simple way of thinking about this is if you can split your distribution in half and fold it, then the two sides perfectly overlap if you have zero skewness. I mean, that would be great. Most of the times on a computer screen, I can't pick it up, fold it in half, and then try and figure it out. but eyeballing it is good when you're just trying to like identify something in somebody else's work. But you should always take a look at exact measures for kurtosis and skewness on actual data if you have to report that for your particular data set. So how does this relate to what we're doing? We're basically assuming that our treatment group and our control group both look like this normal distribution, and that's where we're kind of stopping for now. So what is our parent population for control? It is in green up here. And what is our parent population for treatment? It is in red down here. And that's all we really need to write. This one line in green and this one line in red. And then we get to B. And what happens after B? Well, now is when we start to build our hypotheses. Hypotheses. Okay, didn't add an extra ES in there somewhere, I hope. So your hypotheses for an independent samples design is, you take whatever words that you had for your hypothesis. Maybe it was, I think, my treatment group will be different than my control group. Really simple one. I'm going to spell different as diff. And really, whenever we're building our hypotheses, I shouldn't say the word group. I should actually say the word population, because hypotheses are made about the population. Cool. This here is our research hypothesis, and we want to make statistical hypotheses. And how do we do that? Well, I'm going to make my null hypothesis in red, and I'm going to make my alternate hypothesis in purple. I'm going to call this HA to try to be consistent with what I've been doing so far. And let's just make up our null hypothesis first. A null hypothesis needs to include all of the populations that you are kind of pitting against each other. So I need to include both my treatment and my control populations whenever I'm writing this out. So I'm going to say, okay, what am I trying to study here? Maybe I'm trying to study if the treatment population mean, specifically, will be different from the control population mean. Okay, so what do I need to do in order to specify what treatment population mean and control population mean look like? Well, in the population, we have mu, and I'm going to say that I think my treatment population and my control population in the null hypothesis are going to be the same. Now, depending on your professor or your level of stats, you may see this written simply as mu treatment does not equal mu control, or you may get a little bit more involved with the math. And some people decide to say that, okay, if I want to test for a difference between my treatment condition and my controlled condition, all I would have to do is calculate the average of my treatment condition, subtract the average of my control condition, and check if that's equal to 0. Because if my treatment population mean was, let's say, 50, and my control population mean was 50, there's no difference between them. I would get 50 minus 50 equals 0. And so that's the kind of thinking that's going into this particular setup for this particular hypothesis. If I wanted to set up my alternate hypothesis in the same way, and I have to set my null and my hypotheses up in the same way, what am I going to do? Well, I'm going to say mu treatment minus mu control in the alternate hypothesis are not going to be the same. So they're not going to equal 0 when I take some sort of subtraction between the two. For instance, if my mu treatment was equal to 50, population mean in my treatment group, but the population mean in my control group was 25, cool, well 50 minus 25 is correct. It does not equal 0. It equals 25. And so if this happened to be the truth in the universe, then I would, say that my alternate hypothesis is correct. This is a non-directional set of null and alternate hypotheses. So what I'm going to do is quickly move this down a bit and write the words non-directional above it, and then I'll write a directional version. So let's move this down just a tad. We're going to call this non-directional example. And I'm going to scroll down and do a directional example now. So what about a directional example? With directional examples, you just have to be really careful about where you put the population treatment mean and where you put the population control mean, because it'll make your life very difficult when you're trying to set up your hypotheses. Why is that? Well, let me write out what I have a hypothesis for. So maybe I think that the population treatment mean will be greater than the population control mean. Population control mean. What's that look like? Well, this time around, it's actually easier for me to make my alternate hypothesis first and then my null hypothesis. Anytime you're doing some sort of directional thing, try writing out your alternate hypothesis and then your null hypothesis, because let's start with green again for maybe this time for the alternate hypothesis. When I'm dealing with my alternate hypothesis, I read along with what I wrote for my research hypothesis. I think treatment mean will be greater than population mean, than control mean. Cool. So I will write treatment mean, not treat mean, mint, and I will write control mean. And when I take the subtraction between the two, my alternate hypothesis thinks that my treatment mean, maybe my treatment mean is going to be 50, and my control mean, my control mean theoretically in the alternate hypothesis is that control is less than treatment, so maybe my control mean is 25. When I try to figure out what to put as a symbol between, instead of an equal to or not equal to between my mu control and my 0, I have to think about what it looks like if I take 50 minus 25. Well, if I do that, I'm going to get a number that is, positive in this case. So it will be bigger than 0. And suddenly, what do I get if I do 50 minus 25? Well, I get 25. That is, in fact, bigger than 0. I have set up my hypothesis correctly. What if, let's get rid of these now because they're just examples of theoretical population means. So what if I how do I set up my null hypothesis now? Well, in my null hypothesis, I'm still going to put my treatment, and I'm going to put my control in the same spot, and I'm still going to put that 0 in the same spot. And so what do? Well, I follow the format that I had from below, so I'm going to put a subtraction sign in between treatment and control, and my hypothesis just needs to be the opposite. My null hypothesis sign just needs to be the opposite of the sign I put into my alternate hypothesis. So I would put a lesser than sign, but I would also put an equal to sign. Why is that? because I need to account for 3 different possibilities when I actually go and collect my data. I need to account for the possibility that my treatment is greater than my control, so I'll get positive numbers. I need to account for the possibility that my treatment is less than my control group, where I would get negative numbers. If I did, my treatment group had a mean of 50 and my control group maybe had a mean of 100, I would get negative 50 from doing that. In which case, fitting with my null hypothesis, it's negative, this lesser than sign is correct. But I also need to account for the fact that, well, my treatment and my control group could have the same values. In which case, if my treatment group has a score of, a mean of 50 and my control group also has a mean of 50, well, that gets thrown into the null world. I don't care if my treatment didn't do anything. That's not interesting to me. I also, in this particular directional case, don't care if my treatment actually, reduced scores compared to control. It's not important to me. So I throw both of those into the null hypothesis. In terms of directional hypotheses, you can totally make the opposite direction kind of hypothesis. Maybe you think that your population treatment mean will be less than the population control mean, in which case all that you would really have to do is this. Let me just scroll down a little bit and write that in another color. So, another directional example. I think I'm going to be lazy and just write treatment will be less than control. And so how does that end up working out? Well, I'm running out of colors. I'm going to build my alternate hypothesis first. And it's going to be the exact opposite of the one that was in our previous example. So I'm going to say mu treat minus mu control. Well, if I'm correct and my treatment mean is less than my control group, then going treat minus control will get me a number less than 0. For instance, if my treatment mean was 25 and my control mean was 50, I'm going to get negative 25. And this works for any case where the treatment mean is less than the control mean. I will always get a number less than 0. Cool. What about the null hypothesis? Well, I keep on forgetting to grab my paintbrush. When we're dealing with our null hypothesis, simple enough. We're just going to throw all of the other symbol options into my null section. So let's go ahead and do that. Cool. And so now what we have is, if the null hypothesis is true, then it doesn't matter if our treatment mean and our control mean are the same number. It doesn't mean if our treatment mean It doesn't matter if our treatment mean is bigger than our control mean. That is fitting with our null hypothesis as well. The only thing that's left in our alternate hypothesis is a world in which the treatment mean is somehow, less than our control mean, and that's what we actually care about according to our research hypothesis. So whenever you're dealing with those hypotheses, try to make sure they're formatted correctly for whatever program you're taking, or if you're doing your own research, just make whatever works for you, I guess. Fit with whatever the general consensus out there in the world is, as long as it's accurate. Just try to be accurate at all times, pretty much. But that's it for hypotheses. What do we do after that? Well, there is the test distribution that we have to deal with. Now this is going to sound really weird, but you can actually do a z-test with 2 independent samples, just like you can do a t-test with 2 independent samples, but your test distribution does change for those. Distribution. Go. So what do I mean by those test distributions? Scroll down too far. So what do we have as options? We have options based off of what sort of information we're given. So you have to pick your test distribution based off of what sort of information from the population do you have. So I'm going to just call this what sort of population info available, and then hopefully get to writing other things available. So one of the first things that people kind of start with is our Z distribution, or at least the first distribution they get to learn about is the Z distribution. Z distribution. And there are some rules with that. The most kind of important one at this moment when you're dealing with an independent samples design is you have to know all of the population variances that you have groups for. So you would need to know the population variance of your treatment group, and you would have to know the population variance of your control group. Largely, we assume that these are the same in this kind of scenario, or at least we hope that the treatment that we give to people does not affect the variability. And so there's actually an assumption called homogeneity of variance that you have to check later on whenever you're doing independent samples design, because if it turns out that the variances in your treatment and your control group are not the same, it breaks a couple of assumptions and we need to fix things for that. I'll get into it in a little bit, but know that it's coming up. Now, what if we didn't know the population, treatment variance or even the control variance? Well, then we're stuck not using a Z distribution. We physically cannot or should not use a Z distribution. We should use something else. And so what sort of distribution should we use if we don't know the population variance? Well, we can use the T distribution. And in this case, the T distribution does work because, you don't know the variances in either your control or your treatment. Because if you knew population variances, you would just go zoom over and do a Z test or use a Z distribution instead of bothering with the T distribution at all. If you happen to know population variances, all of your data analysis work is going to, or at least it's assumed to be, more accurate, because you don't have to estimate the population variances with potentially small samples, and small samples don't give very good estimates of population information. So if you're good and you know the population information, go use a Z distribution for a Z test. If you don't know the population variances, you're stuck with the T distribution, and so good luck. So I'm going to decide that for examples we're going to use the T distribution because this is most often the case. Especially in research. I've always used my T distribution and my T test when I'm doing independent samples design because I simply didn't have any population information. And so there's no point in even going for a Z distribution in that case. So in this particular case, examples will use the T distribution. Cool, so we have essentially just picked our test distribution based off of one very key piece of information. It does also help that we've assumed normality. So both of these, definitely, you're going to want continuous data. For both Z distributions and for T distributions. And continuous data means that, it's like interval and ratio data. You can keep dividing the units down into smaller and smaller quantities. But technically you can get interval or ratio scales that, stop being able to be divided into smaller and smaller quantities eventually. shoe size, for instance, you can get a size 8.5, but unless you make it yourself, you can't get a size 8.25. So it's technically like kind of continuous data, but we should really just call that interval data and ratio data. I'm going to write that on the other side as well because it's the same thing. So we want continuous data, and we really want just interval and ratio data when we're dealing with the t and the z distributions. So I'm going to have, whatever examples I come up with, they're either going to be on an interval or a ratio scale, and they're going to use the t distribution, and I'll probably repeat that throughout. But we are done picking our particular distribution, and we're going to move on to the decision criteria section. Okay, so for that decision criteria section, what are we going to deal with? Well, this is going to be step D. First, we have to write it all down. So, with decision criteria, we do have to decide, what is our type 1 error probability going to be set at? And we're going to call that alpha, just like every other time that we set it. And maybe you've decided that your type 1 error probability is going to be set at 5%. Now, the way that we usually write this is actually alpha is equal to 0.05, so we're writing it in terms of proportion instead of percentage. I'm just going to say that these are the same number, just as a percentage versus as a probability or a proportion. Cool. So, of course, don't forget the type 1 error probability, 5%, 10%, 15%, 2%, 0.5%. That is all going to depend on the issues that you might have if you make a false positive, a type 1 error. And if your type 1 error could potentially kill somebody, you're going to want to really carefully consider what your percentage or proportion is going to be. Now, more difficult would be the type 2 error. Probability and what you set that at. And there's actually quite a lot of probability of thought that has to go into dealing with type 2 error probability. Now remember, we're going to call this beta, and essentially we don't know what our type 2 error probability is going to be without making a whole bunch of more assumptions. So what I'm going to do is at the very end of this, I'm going to talk about it later, talk at end of video, because it's kind of a nightmare to deal with right in the middle of here. The useful thing that dealing with type 2 error probability is that you can use it to set how many participants in each group you're going to need. Usually used to estimate. There's a couple of things that it's used to estimate. One, number of participants that you need to see a certain size of effect. And that will delve us into a whole another thing at the very end of this about what effect size is, which I'll get into. But it is a very important thing to consider because maybe you have what's known of as a small effect. Your treatment only affected participants by a little amount, not a large amount. And little effects are actually hard to see when you only have a few participants, because with few participants you end up with quite a bit of sampling variability, or at least the potential for sampling variability. And so you're penalized for that when you only have a small number of participants. So if you know how many participants are needed to see a small effect, then you get rid of some of the uncertainty of, but is it really there? Or did I make a type 2 error? Did I accidentally screw this up and I couldn't find anything? And so it is useful to deal with type 2 error somewhere before you collect data. For instance, if you deal with this and you do something called a power analysis, that's going to be another video because it's a nightmare. Then, once you do your power analysis, it'll tell you, hey, maybe you need 20 participants per group to see a large effect, or you'll need 50 people per group to see a medium effect, or maybe even 937 people per group in order to see an itty bitty tiny little effect that only affects the treatment mean by a little bit relative to what the overall variability is. But in terms of making a decision right now, most people end up just looking at their alpha levels and then going and collecting as many participants as possible, which I sincerely hope research is changing and people are seriously considering power analyses and figuring out the number of participants that they actually need to see a certain sizes of effect, at least according to a bunch of assumptions made ahead of time. So, our decision criteria for this really just boils down to set alpha for now, and then if you're in like a first level undergraduate data analysis program, this is pretty much where you stop. If you're in the second or the third levels, or if you're in grad school, please think about power analyses, which again, totally another video. So we've set alpha. We've set the probability of making a type 1 error at 5%. Cool, that's basically what our decision criteria is. Now, for decision criteria in regards to a t-test, that's pretty much the same as if we had done a first Z test, so we're all good there. So what I'm going to do now is move off of decision criteria and move on to the stage that we never want to forget, which is E, collect some data. And it's always good to consider how you're going to collect data before you actually go and do it, because you may find out that, the way that I plan to collect data actually involved intermixing both my treatment and my control group, and that's not going to work for an independent samples design. So the way that you have to collect data is you're going to have this nice cloud of participants, or at least of a population. And what you're going to do is randomly these people are going to walk into your lab and you're going to assign them to, group 1 and group 2. We often don't want to let people know which group they're in, so we don't necessarily want to tell them that group 1 is actually the treatment group and group 2 is actually the control group, unless it's absolutely necessary. Or your ethics committee is quite harsh for not doing that. But essentially, this population will walk into your lab and you're randomly going to assign, one person to your treatment, another person to your control, another person to your treatment, another person to your control, until eventually they just start stacking up and I stop wanting to draw things. So we're going to pretend that we have 10 people in each group and they are completely separate people. Totally different. So imagine that, for a more concrete example, we're going to deal with the population of huskies. Huskies are a kind of dog. They shed an absolute massive amount, and maybe we're trying to test if group 1, our treatment group, was a particular dander shampoo that said that it would reduce the amount of shedding. And group 2 is just our control group. They get regular shampoo and they say absolutely nothing about the amount of shedding that huskies are going to go through. So what do we do with this? Well, we've collected data, we've taken random roughly, 20 huskies, put half of them into our treatment group, gave them the dander shampoo, gave them back to the owners and said, now keep track of how much dog hair is being shed by your husky. And in group 2 we did the same thing, except all we did was give them a regular shampoo and then give them back to their owners and say keep track of how much dander or shedding they're dealing with. And that's it for the collect data stage, where we collect all of that information about how many pounds of fur this, a given dog had, and maybe what we ended up with was, making up numbers is always bad on the spot. Maybe what we ended up with in the dander shampoo area was a bunch of scores like this. And so what I'm going to build is a data table for group 1. So dog 1, dog 2, dog 3, dog 4, dog 5, etc. And we're going to say this is in grams of dog fur shed that particular, month. And for the first 5 dogs, we're going to make up a whole bunch of data, and then I'm just going to go ... because I don't want to make up any more data yet. So our first dog maybe shed 400 grams, our second dog shed 300 grams, our third dog shed 400, our fourth dog shed 500, and our fifth dog shed, I'm lazy, 400. And then if we go, you can probably hear laughter in the background. I have no idea why. My house is just crazy. Let's go to group 2. This is, of course, our control group, and we're still measuring in grams of dog fur because our dependent measure does not change between our 2 groups. It's still the same dependent measure. So, dog 1, dog 2, dog 3, dog 4, dog 5, and then etc. dogs. So maybe the first dog shed 800 grams of dog fur in a month. Oh my goodness, I don't even want to weigh that. Our second one shed 700, and then 600, and then 700, and then 700 again, and then we'll just pretend I made up more data for the others. So this is where I have collected, all of my data, and I'm essentially done with this step. The next step that we're going to deal with is step F, and that is calculate things. If you happen to have data from your population, you can calculate parameters. If you happen to have data from your sample, you're going to be calculating statistics. So if you have population data, you're going to, we're going to throw in parameters here. I'm going to have to really figure out what is so funny downstairs. And if we're dealing with sample data, we're going to be calculating statistics. Cool. I'm going to be calculating statistics here because I don't have any population data. I don't know the population mean. I don't know the population variance. I didn't collect the entire population of huskies when I was doing my my collect the data step. And so I'm just going to be, for examples, for subsequent examples, I'm going to be calculating statistics. Saying I've got sample data. So what do I need to calculate for this? Well, there's two kinds of things that I need to calculate. One is going to be my descriptive statistics. And for the descriptive statistics on an independent samples design, you actually have to calculate descriptive statistics twice, because you must calculate your descriptive statistics. Let me just scroll up so that I can figure out what colors. Red and blue. Cool. For our treatment group and for our control group separately. make sure that you calculate your group 1 score, averages, variability, etc. differently from your group 2 averages, variability, etc. And so maybe I'm going to pretend that I actually looked back up there and made up some more data, but I'm going to pretend that I calculated the average of my treatment group as, okay, I'm going to scroll back up there and get a hint, 400 grams. And I'm going to pretend that in my control group, I have an average, let's scroll back up, of 700 grams. It's a lot of dog fur. I feel sorry for people with allergies and huskies. And so, cheers. Now what we have to do is continue, making these descriptive statistics for each group. We need to calculate possibly things like the median. We need to calculate things like the mode. But one of the most important things that we're going to need to calculate for both of these groups is the standard deviation and the variance. And that's because when it comes to independent samples designs, how we calculate things, how we get something called degrees of freedom, which is en route to how we make a decision, it depends on whether or not we have homogeneity of variance, where we have the same amounts of variance in both of our groups, or if we have heterogeneity of variance. And essentially, in order to make life easier for yourself in pretty much every single research thing that you're doing, having homogeneity of variance makes the math slightly easier, it makes the understanding slightly better, and it makes the things that you say about your data and the inferences that you make to the population more accurate, because, or at least we hope it makes it more accurate, because having homogeneity of variance is an assumption of doing something called the independent samples t-test. So if you don't have homogeneity of variance, you've done what we like to call violated an assumption, and now you have to figure out how to fix it. And those fixes there are many different fixes, all of them with different effects on sort of, how conservative or liberal do you want to be in your fix, how about your description of things, and there's a whole bunch of things that you really want to consider. So to make your life easier, pretend that you always have normal data, but double check it just in case you don't, because it might turn out that you have to apply one of these fixes, and then you get to have fun going down a stats rabbit hole. That may be another video. Stats rabbit holes on homogeneity of variance and heterogeneity of variance. So at this point, for my descriptive statistics, what I'm going to do is set things up so that I can show you side by side what happens when you have homogeneity of variance and heterogeneity of variance. So we're going to label things. Over on the left here, we're going to have homogeneity of variance, and I'm probably saying it wrong, but I really don't care, and of variance. And over on the right, in red, nope, we already used red recently, we're going to use darker blue. Nope, that's our control group. We're going to use friggin' light purple. And we're going to say on the right side is heterogeneity of variance. And I'll draw a couple of things to show you what that would look like. One of the simplest way to figure out if there are weird things happening in your data is to literally have some sort of graph depicting your data and then to look at them. So the data that we have here, we have two groups. So I'm going to focus on the homogeneity of variance section first. So in our groups, what I'm going to do is I'm going to draw our treatment distribution, and I'm going to draw our control distribution. So our treatment distribution and our control distribution, we've been using red for treatment, so I'm going to stick with that. And let's pretend that we had this kind of distribution in our treatment group with a mean in our sample of, was it 300 or 400? 400. And then what I'm going to do is I'm going to draw in blue, because we've been using blue for a control group, what's hopefully going to be exactly the same one, and it looks close enough to being the same one. It just happens to have a mean in the control group of 700. But the width of the distribution, the variability around the mean, is going to be the same for both of these groups. So we're going to consider the standard deviation of both groups to be 100. And magic, you have homogeneity of variance, because these numbers are exactly the same. I just drew the population version here, so I'm going to swap that out and make sure that I put the sample symbol. Now the sample symbol is just an S. So that means standard deviation. If you see S squared, that means variance, and you would have to square root it in order to get the standard deviation, or you would have to take the standard deviation and square it in order to get the variance. So, do we have homogeneity of variance? Well, if I look at my variance in my treatment group, it is equal to the variance in my control group. Cool. There is a little bit more to this if you want to keep going. Essentially, there's a rule or an heuristic, honestly I don't know how to say it, a heuristic on how to figure out if you do have homogeneity of variance. Because not all the time are you going to find, oh, I've got a standard deviation of 100 in one of my groups and exactly the same standard deviation of 100 in my other groups. Maybe you'll get 99 in one group and 101 in the other group. What are you supposed to do? Well, if you have equal sample sizes or equal n's in both group, what you do is you take the variance that is larger divided by the variance that is smaller, and you're hoping that that number is less than 4. If, for instance, we ended up with a variance in our treatment group of 100, and we ended up with a variance in our control group of 28, well, let me pull up a calculator. 100 divided by 28 is going to get me 3.5714, and then I'm going to give up after 4 decimal places. But that is less than 4. 3 point, and then I don't have the short-term memory in order to deal with this properly. 5714, 5714. Cool. So, in this particular case, I would say, yep, I've got homogeneity of variance. What happens if you don't have equal sample sizes in both of your independent groups? One of the dogs ran away and the owner went and got him and then didn't bring him back and then didn't tell you how many, grams of dander there were. And so you might have 9 dogs in one group now and 10 dogs in the other. So what do we do when we have unequal sample sizes? Well, we basically do the same thing. We take the larger variance, we divide it by the smaller variance, and now we're looking for a number less than 2. So when you don't have equal sample sizes, it actually gets a lot more difficult to say that you have homogeneity of variance, because you have to make a more conservative comparison in order to say, hey, yeah, I have homogeneity of variance. If you have equal sample sizes, your comparison number is 4. If you have unequal sample sizes, your comparison number is 2. Good luck. I would have to have a much smaller difference between my larger and smaller variances in order to say, yep, I've got homogeneity of variance. Cool. That's if I have homogeneity of variance, and how do I figure out if I have homogeneity of variance? So let's try to figure out what it looks like if we have heterogeneity of variance. There are actually a lot of different ways that you can have heterogeneity of variance. It basically just means my variances are different between my two groups. So let's pretend that we have this as our treatment group with a mean of 400, and I'm going to pretend that I have a a standard deviation of 100 again, 100 grams. Now let me go and draw my control group. This is now my control group. It's going to have a mean of 700, and it's going to have a standard deviation of, what am I thinking? 450. On average, dogs shed around 450 grams around the mean, so they go from 700 up 450 points, and from 700 down 450 points on average. And just visually, these don't look like they have the same variability at all. One of them has more variability, one of them is even positively skewed. And so we would try to do that math. We're going to pretend that we have equal sample sizes in this case. So if n's are same, what do? Well, I'm going to do my larger variance, which is 450. And I'm going to divide that by my smaller variance, which is 100, and I'm going to get 4.5. We're going to pretend these are variances now. F it. These are all variances now, because I keep using the wrong number. So, larger variance over smaller variance, smaller, and that's just how you figure it out. If you have, hey look, heterogeneity of variance. This number here is 4.5. That is not less than our heuristic comparison for equal sample sizes of 4. So I have to say, oh no, I have heterogeneity of variance. Alright, so once you've decided if you have heterogeneity of variance or homogeneity of variance, and you're either very unhappy or you are happy because, if you're at homogeneity of variance, at least looking at SPSS is relatively simple. You don't have to do any fixes for your output from SPSS, or even your output if you hand calculate anything. And eventually, we're not going to have to play with our degrees of freedom in order to account for the fact that we might have heterogeneity of variance. So in terms of figuring out where to go from here, we're actually going to step away from the descriptive statistics, and there are many more descriptive statistics that you can have. You could have more than just the mean, the median, and the mode, and the variance. You could have the standard deviation, the range. You could have your skewness and your kurtosis, which would be great here as well, so that we could tell if we have skewed data, or if we have some sort of kurtotic data, or if we don't have those sorts of things. It's also great to tell people if you have one mode or two modes. So do I have a unimodal distribution, or a bimodal distribution, or a trimodal, multimodal distribution, in which case have fun. But don't forget to describe all of those lovely things, including sample size, during your descriptive statistics. So what I'm going to do now is scroll down and focus on the terrifying inferential statistics, or inferential data analysis part. We had to figure out what test statistic we're going to do. I'm pretty sure that was step C. And so we're going to look back at step C to figure out what distribution we were dealing with. So I will literally just zoom out and then zoom into step C, A, B, or C, and I said examples will use the t distribution. Okay, so that's good. At least I don't have to, figure that out now. That's why I did it ahead of time. And so it specifically said that I will be using the t distribution. That means that the test type I'm going to be dealing with is known as a t-test. Specifically, of 2 independent samples. Okay, so with a t-test and a t-distribution, you do get a bunch of t-critical values off of this, and the entire point of these t-critical values is to help you in the decision period as to whether you should reject your null hypothesis and say, hey look, I actually think I found something, or if you're going to retain your null hypothesis and say, you know what, I don't think I have enough proof to say that I did find anything. Basically saying, oops, I didn't find anything. And the t-critical values are going to be based off of a couple of things when it comes to t-tests. So I'm just going to scroll down and list those things. And I'm going to use green, and we're going to say that, okay, let's take a look at this t-table. In order to look up information on it, you're going to need a few different things. You need to know if you have a non-directional or a directional hypothesis. In this hypothesis, you need to know what your type 1 error probability is, so your alpha, your false positive rate, type 1 error probability, false positive. And what else you're going to need to know? Well, I can look at the table, and it's going to say something on here about degrees of freedom. Let me just zoom in. I have this table from a textbook that we were using at one point during data analysis courses, and I just keep using it. Essentially what we have here is a set of headings that tell you, if you're using this for a one-tailed test versus a two-tailed test. Yes, I want to draw in orange. A two-tailed test, but I don't want it filled with anything. There. Alright, I give up. Is a one-tailed test here. Mother of all. Goodness. So on this t-table here, you're going to find a few things. You're going to find this header called level of significance for one-tailed test with an alpha 1 tail. Don't worry about that little thing. There's also level of significance for two-tailed test. Again, it's got like this little alpha 2, which is going to be different from your alpha 1. Essentially what these mean is if you're interested in using a one-tailed test, you're going to have alpha set at a particular level, and it's going to hold itself in one particular tail. If you're doing, a two-tailed test, you actually have two sides to your distribution that are of interest, and your alpha is going to be split amongst two different sides, and what essentially happens is you do some fun math with the numbers that are in here, and you really don't need to worry about it at this point. So don't worry about the little things that you may not recognize on this t-distribution or this t-table if it's somehow different from your own. I am using one that splits up one-tailed test from two-tailed test. I'm not going to use one from the internet that clumps everything together and makes it a nightmare. So what do we have on here that we've already dealt with? Well, we've dealt with one-tailed versus a two-tailed test. Already, maybe we can remember from one of our hypotheses that we were doing a non-directional thing, and we'll say right now that we're doing a non-directional hypothesis. I also, in step decision making, I think that was step E or D, what I did was I set alpha rate, and so what we have is another set of headings in here that tell you, okay, this is the alpha level, but only for a one-tailed test. Whereas this one down here is your alpha level, but only for a two-tailed test. So when I set alpha at 0.05, I just have to say, oh, I was doing a two-tailed test, and here's my alpha of 0.05. And now I have one column that contains a whole bunch of critical values. These are cutoffs, and they are based off of something called degrees of freedom. You can find this column all the way to the left that has a header df, that is degrees of freedom. And there are numbers starting at 1, and they increase until your table gives up, essentially, and can't calculate the difference between a 0.2 and a 0.1 at a very large degrees of freedom. And so the last thing that essentially we need when we're using a t-table is degrees of freedom. And now this degrees of freedom thing is really annoying. It's hard to explain for a lot of people without just referring back to the standard deviation. And what it essentially is, if you're interested in this, otherwise you can probably skip forward to where you actually get the formula. We spell this degrees of freedom, and essentially you have degrees of freedom whenever you're estimating the population variability, because you don't have the population variability. Now, here's where you stop, because I'm going to give you the formula for independent samples. Dependent samples. Don't ask me, I don't spell well when I talk. Samples, t-test specifically. Your degrees of freedom is going to be equal to, actually I'm going to rewrite that because it's long. Your degrees of freedom is going to be equal to the sample size of your first group minus 1 plus the sample size of your second group minus 1. Okay, that seems pretty easy, and it kind of is. Essentially, whenever you have one of your groups, your, what color was it? Red. Oh no, I used the wrong color. So how do I have an example for this? Let's say that I'm talking about my treatment group. That's the one where we gave dogs shampoo that is theoretically going to reduce their dander and their amount of shedding. And we have 10 people in it. So, okay, well, in order to calculate this first part of degrees of freedom, I'm going to say, okay, well, n1 minus 1 is just 9, so I have a degrees of freedom here. And then what I have to do is go over to my control group. And this is the second part of the formula over here. And we're going to say, well, n was equal to 10, theoretically, and then I got too lazy to keep writing things. And we're going to say that n2 now, minus 1, is equal to 9. So what we're going to end up with is something called degrees of freedom, sorry about the wonky coloring, total. Because each group separately has a degrees of freedom for the first group, and this separately is the degrees of freedom for the second group. And then when you add them together, oh no, I'm running out of space. And then when you take df1 plus df2, you get df total. So totally your way of dealing with how you get degrees of freedom total for this. But essentially what we have to do is we have to take into account the fact that, and I'm going to start scrolling up so don't get sick, the fact that we don't have any idea what the population variability is, and both our treatment group and our control group are estimating their own separate population variabilities. So treatment, control, just gonna keep doing that. What do we have in the treatment group? We are estimating the population variance, the population standard deviation, it really doesn't matter, in the treatment population. But because we don't have every single husky in our treatment group that has ever been born and has ever been measured for how much dog hair they give out on a yearly basis, monthly basis, we have to use the sample standard deviation, or the sample variance. And now what really happens here is we only have 10 dogs in our sample. Is that going to be very accurate at estimating the population variability? No, probably not. You're like, well, are you going to tell me, or are you just going to keep writing or forget you asked a question? No. So if you have 100 dogs, is that accurate? That's a little bit more accurate. It might not be 100% accurate. But if you had, that's like 100,000 dogs, A, I hope you don't have allergies, and B, you're going to get very accurate at, whoops, too many R's and not enough C's, accurate at determining what the population variability is. And so what you end up with is, when you have small sample sizes and you subtract a particular value from it depending on what kind of test you end up with, for us, we have our sample size minus 1. And so if we only have sample sizes of 10, that's really going to affect our values compared to if we had 100 people in it. So n minus 1 wouldn't affect the value as much, and n, if we had 100,000 people, or 100,000 dogs, sorry, and we subtracted 1 from it, then, you know, it's not going to affect whatever final value we're using sample size minus 1 for, compared to if we had a small sample size. So that is essentially what degrees of freedom is telling you. If you have a very small sample size, degrees of freedom is going to screw things up royally for you. If you have like 3 people, then it's really going to screw things up. And B, it's actually telling you the number of items in your sample that are free to vary being in quotation marks, given the, you know, outcome that you got. So that's going to be very cryptic. What do we actually mean by that? So degrees of freedom, the number of items in your sample that are free to vary given a certain output or outcome. So I'm just going to write outcome. So what the heck does that mean? I've seen this described in a couple of different ways, and it's always very difficult to do so. So I'm going to do it in both ways, and you're free to skip over both of them. So what are they? Way 1 is in bluish. So what we have are 7 hats. Blue hat, red hat, checkered hat. Okay, I'm getting too invested in hats. We have green hat. We have rainbow hat. This one's going to take me a second or two. Roy G. And I don't know where blue and violet are going. We have 1, 2, 3, 4, 5 hats. We have a brown hat. And we have a white hat, but I can't draw that, so I'm just going to draw it as black and not color it in. So what do we have here? We have 7 days of the week. Alright, so we have Monday, we have Tuesday, Wednesday, Thursday, Friday. Uh-oh, it's gonna zoom out. We have Monday, Tuesday, Wednesday, Thursday, Friday. We have Saturday, and we have Sunday. Usually I start the days of the week on Sunday, but apparently I screwed that up. And maybe on Monday you decide that you're going to wear the red hat to work, and then it's a very terrible hat and it completely disintegrates. On Tuesday you wear the green hat to work. Well, you at least get the colors right. And then it disintegrates and you don't have a green hat anymore. Cool. On Wednesday, what do you have? Wednesday you're going to wear the blue hat. And there it goes. And what other hats do we have? We have the white hat. On Thursday, we're going to be good on Thursday. Friday we have the brown hat. Rainbow hat goes on Saturday. And on Sunday, we didn't have a choice about what hat we have to wear on Sunday. But for all of the other ones, we actually did. We chose, I was taking my sweet time trying to pick a color between what colors were left here. So on Monday, I could pick between red, blue, rainbow, checkered, brown, white, whatever. But on Tuesday, suddenly I couldn't choose red anymore, and so I was missing a free value. Sunday is the only day in which you have 0 choices, and you must wear the checkered hat. There's no choice left for that last value. And so when it comes to degrees of freedom, it is not free to vary. Your very last number, given a whole bunch of certain outcomes, is not free to be whatever one of these hats it wants to be. It has to pick whatever's left in order to make up the difference. And that's kind of the whole point about the free to vary thing. It makes up the difference between whatever existed out there and whatever it is now. And the other way to explain this is using math, and so if you've got a crippling fear of math like many psychologists, no, not many psychologists, but many psychology students, sociology students, criminology students, social psychologists, the general area of, I went into this class to avoid math. I didn't think that I'd had to have to do data analysis as part of it. Don't worry too much, you can skip this. So, what do we have here? We have a sample mean. So I'll use either this. No, you know what? That's going to be too confusing. I'm just going to keep using X bar. So we have a sample mean here that is equal to 10. But I lost all of the data. All I know is that I had 5 people in my data set. Their sample mean was equal to 10, but I don't know what the actual values were. So let's say that I wanted to remake what the sample mean was using some numbers. And so what I would do is I would make a fake data table, and I would go, okay, we're going to have participant 1, and they are going to get, they're going to get 11. And so you say, okay, well, my data set now consists of 11. What about participant 2? Well, I'm going to pretend that they got like 19. Okay, well, 19. That doesn't look like the average is equal to 10, but okay. What about participant 3? Well, participant 3 got 1. Okay, well, now we're starting to even out a little bit. And, number 4, maybe they got 22. And now we're going to wait, 22. If the average is 10, what did participant 5 have to get? Is participant 5 free to be whatever it wants if the average of these numbers plus whatever is left is equal to 10? No, it has to be something that makes up the difference between, let me do this for us. It has to make up the difference between 11 plus 19 plus 1 plus 22 plus something that will make the average equal to 10. And so right now, when we add up our first 4 numbers, we end up with a score of 53. So if I just add up these ones, I get 53. Now, if we want to take the average of those 4 numbers, we can. Oops, there it goes. I wanted the calculator, I didn't want the goodbye paint. So what's 53 divided by 4? if you can do this in your head, you are far better at math than I am. 13.25. So 13.25. The average of those first four numbers is 13.25, but when I have the last value, the number has to equal 10 for the average. Now, let's figure out how, because I made this up in my head, and that was a mistake, because now I actually have to figure out what that last number is. Great. So how do you figure out what that last number is in 10 seconds or less? Well, the way to do that is by taking this sample mean, multiplying it by your sample size, and that will tell you what number needs to be divided by 5 in order to get your average of 10. And so what we want to do here then is sample mean equal to 10 times sample size equal to 5. That's equal to 50. What do we need now? Well, we're obviously going to need 50 divided by 5 to get our sample mean of 10. And that means that we need to take this 53 up here that has been divided by 4, but that's irrelevant now, and we need to make that 50. And so the only way to do that is by going and saying, okay, 53 plus negative 3 is going to equal 50. And then when I divide that by 5, I get my average of 10. So this last value here is not free to be whatever it wants. It has to make up the difference between all of the other values. If you know another way of explaining this, feel free to comment. If this was absolutely unhelpful, feel free to comment. Now, where was I? I was explaining degrees of freedom, and fortunately, here's where you can jump back in if you left. So we need to calculate the degrees of freedom for control. So you are estimating the control variance in the population, but it has to do that using whatever value you've given it in terms of your sample size, and it has to use the sample variance. And so all I've done here now is listed that, hey, look, this is our first degrees of freedom, and this second one, n2 minus 1, is our second degrees of freedom. Cool. Great. So now that we've done all that, we can finally finish calculating degrees of freedom total. So I'm going to scroll down all the way past this stuff, and I'm going to put a rejoin here, sign, so that you can jump to it. Cool. And so let's go ahead and calculate degrees of freedom total again. Great. That would be n1 plus n2 minus 2. That's another way of doing it. It's a way of combining the two. Otherwise, you can do it as n1 minus 1 plus n2 minus 1. Cool. So I pretended that we had 10 dogs in our first group, so we're going to subtract 1 from that, and that we had 10 dogs in our second group, and we had to subtract 1 from that. And so what we're going to do now is scroll our way down and say, cool, we have 9 plus 9, that gets us a degrees of freedom total of 18. What are we going to use that for, I wonder? Well, what we're going to do right about now is I'm going to grab us our critical values. If we had, say, homogeneity of variance, and what we're going to do with that is we're going to say that, hey, for a non-directional hypothesis pair, null and alternate, we're going to use alpha equal to 0.05 or 5% probability. And we're going to use our degrees of freedom total of 18 in order to get our positive and negative critical values, because when we're dealing with a non-directional hypothesis, we don't know which way this is going to go. If we take a look at the t-distribution, we're going to have critical values on the positive and the negative side, because we don't know if this is going to go down or up. This is a little 18, by the way. We like to write our degrees of freedom next to our t when we're drawing a t-table. And so 1 is somewhere around there, -1 is somewhere around there, here's 0. We have +2, we have around -2, not to scale at all, +3, -3, and I'm going to head back to our t-table. And we're going to go ahead and just erase the whole thing, at least part of it. Yeah, okay, that's good enough. We're going to also circle now our non-directional thing, so we're not going to be looking under this section at all. I said we had an alpha of 0.05, so we're not going to be looking in any of these sections at all. And now I have to take a look in the column degrees of freedom for 18. So this keeps going up, 15, 16, 17, 18. Here's where 18 is. I said I'm not interested in these, or these, or these, or these. I have so much erasing to do. Now I'm going to trace over to the column that I am interested in. And I get 2.101. Cool, those are my critical values. 2.101. Where do I draw that? Somewhere on here? Well, I'm going to draw my positive 2.101 somewhere around here. I'm going to draw my negative 2.101 around there. And now what I'm going to do is I'm going to color in the area if I had a non-directional hypothesis with 18 degrees of freedom and a and an alpha of 0.05. This is where I would, from less than -2.101, this is where I would reject my null hypothesis. Anything above positive 2.101 is where I would reject my null hypothesis. But anything in the middle here is where I would fail to reject the null hypothesis, because that positive and negative 2.101 signifies the area in which we would reject our null hypothesis, but really it's the probability of making a type 1 error, a false positive, and on a distribution, that area is always in the extreme scores. So if I happen to get a value on a t-table that's perhaps, let me just write something really quick. If I happen to get a value on this distribution that is very, very rare, even if, my dander shampoo did not reduce dog hair shedding, I could theoretically get a number that's very high up here. If my dog shampoo didn't do anything, it's a very rare score. In fact, it's even more rare than what I said my number of type 1 probability of type 1 errors was going to be. And so I would make an incorrect decision if the null hypothesis was true. If I got a number in here, though, I would retain the null hypothesis based off of my level of uncertainty that I'm willing to take. And that's really what alpha is. It's the level of uncertainty that you're willing to accept in your decision in terms of a type 1 error anyway. And so I like to draw this sort of thing because it helps me remember and it helps me make a decision at the end of a very long exam or an assignment in a way that I don't have to think too hard about, or it could just take me 2 seconds and I get 1 extra mark. So as a TA, drawing this for certain professors gets you more than 1 mark. Up to, I think, 5 marks on certain professors' exams. So, yes, I know who those professors are, and no, I'm not going to say. But that's for a non-directional null or alternate hypothesis. What about for a directional one? Well, I still have to follow the same steps. I'm still using that alpha of 0.05, 0.05, or 5%. And I'm still going to be using my degrees of freedom total of 18, but my critical values are going to change. Let me just scroll up again. These things here are called critical values. They are t critical values. Here, we don't actually have two critical values. We have one critical value, and if it's positive or negative depends entirely on which direction your directional alternate hypothesis was in. And so, how does this work? Well, if I'm going to have two examples here. Example 1 is where my alternate hypothesis said if I take my treatment mean and I subtract my control mean, I'm going to get a number greater than 0. And so in that particular case, if treatment minus control, if dog hair shampoo increases dander minus dog hair shampoo doesn't change dander, well, that would support my alternate hypothesis, apparently, if I was doing a directional one. And so I would be looking for a number greater than 0, and what is greater than 0? Positive numbers. So I would be looking for a t critical value that was positive. I'm just going to call this t crit val equal positive number. On the other hand, if I was, what's the color of this? Hopefully not colorblind. Example 2. If I had the opposite directional hypothesis, where I'm thinking that the treatment mean minus the control mean gave me a number less than 0. Well, that's kind of like how I think my dog hair shampoo actually does decrease the amount that a husky sheds. If I subtract it from the average amount of what a husky sheds, then I'm going to get a number greater than 0, because treat less than control, well, what do you get when you subtract a small number and that minus a big number? You get a negative value. And so the critical value that I'm interested in this particular case would be negative. And I'm going to write this in purple. You can only have one. You can only have either a positive critical value or a negative critical value. So either or negative, not both. Please do not make both direction hypotheses. I am only making both of these hypotheses because I want you to know that you can in fact make a directional hypothesis where you're expecting a negative number, and in a completely different experiments, you're making a directional hypothesis that you can expect a positive number. Don't make the same predictions for one data set unless you have many dependent variables or things that you're looking at. So let's go look up if we have this degrees of freedom of 18, we have a directional hypothesis, and we're using an alpha of 0.05. Well, this is going to be really fun. Area highlight. I want to area highlight all of this. That was not what I wanted to do. Let's hope Control Z a whole bunch of times works. Yes. Alright, so we have a directional hypothesis now. I'm going to go grab my pencil, I'm going to color in a different color, and we're not interested in this two-tailed test thingy anymore. We're totally disinterested. And my PDF reader crashed, so we're only interested in the level of significance for a one-tailed test. On top of that, we're specifically interested in the level, of our specific alpha. So what do we have to do now is just scribble all of this other stuff out that caused my PDF reader to crash. And then we're going to zoom in and try to find our degrees of freedom total. And what's our degrees of freedom total? Well, it's 18. Now I zoom in and we look for the line of 18, and that is 1.734. Okay, so we have, in one case, positive 1.734, and we have in another case, I don't remember what color it was, 1.7 3, 4. That's negative. Just make sure that you take a look at your alternate hypothesis and figure out which of these two cases you're dealing with, and then specifically write out which positive or negative critical value you are using. Cool. Now that we have our critical values, I have to get back into the difficult stuff, because we've been talking about critical values and degrees of freedom if we have homogeneity of variance. If we don't have homogeneity of variance, there's a bunch of fun stuff that happens to degrees of freedom. I'm not going to write out the formula because it's absolutely terrifying, and honestly, it's not something you should calculate by hand because of the possibility of error, but it is something that you should know happens to your degrees of freedom. So I'm going to scroll up and go and say one more line right about here and say, if you have heterogeneity of variance, your degrees of freedom is adjusted. You can find these values, if you have SPSS and you're using it to analyze some data, if it detects and you have to specifically look for heterogeneity of variance, you do have to use whatever adjusted degrees of freedom they give you in order to look up your critical values, and those degrees of freedom often contain decimal places. This degrees of freedom is always going to be less than, this is going to be called degrees of freedom adjusted. It's always going to be less than your degrees of freedom total. Now, why is that? Less than. Why is that? That's because when we decrease our degrees of freedom, we actually make it harder to reject the null hypothesis. And that's because when we have, this is going to use our DF adjusted on the left. I'm going to build us a t distribution using it, and then on the right I'm going to build a t distribution using a degrees of freedom total. If I have homogeneity of variance, then I'm going to have a nice t distribution where I have the center at 0 and most of the scores piled up in the center, because when I have a degrees of freedom total of perhaps 18, this is naturally what a t-distribution looks like under all of the adequate assumptions. Adequate enough of sample statistics piled up in the center, and fewer but not no sample statistics piled up in the tails. Cool. What if I have not gotten homogeneity of variance? What if I actually have heterogeneity of variance? Well, what happens is that assumption is violated, and when we have a t-distribution, it only operates under specific assumptions. And if you don't have those assumptions, the t-distribution is no longer accurate at telling you what the probability of obtaining a particular statistic is in the null distribution. It's now giving you what it thinks, you would get if you had homogeneity of variance, but you don't. So you need to adjust your degrees of freedom and make them smaller, because what making your degrees of freedom smaller does is it widens your t-distribution. So here is where 0 is, and what you have now is you've got more people in the edges because your statistics are now more spread out, because your degrees of freedom has been adjusted to a smaller value, and that assumes that you have used a smaller sample size in some way. This is probably incredibly complicating until you start taking possibly higher level data analysis courses. So if you're in first year and you're going, I have no idea what you're talking about, skip it. Unless it's been quizzed already, in which case don't skip it. So what does essentially flattening the curve. So this one is higher. So I'm going to write some things out. This is higher, more values in center, whereas the one on the left is lower peak. And this also needs the word peak. It's got a lower peak, and there are more values, perhaps, away from center. Cool. It also makes sure that we have more difficult critical values. So that's another thing. Critical values are more extreme. Whereas if you don't have an adjusted degrees of freedom, if you just have a regular degrees of freedom total, then what you end up with is just critical values that are normal for that particular degrees of freedom. Please note that this is all like normal is shorthand, not in the sense of normal distribution. They're just where they're supposed to be. We're going to pretend that we have homogeneity of variance, so I don't have to do the math for degrees of freedom adjusted. If you do need the math for degrees of freedom adjusted, I will paste it here later. Or right now, actually, because you're watching this. Cool. So, we actually aren't going to be using our degrees of freedom adjusted. We're going to be using our degrees of freedom total. We're going to say that we have our critical values already. Let me zoom back to them. And if we have a directional hypothesis, we're going to be using either positive or negative 1.734, whereas if we have a non-directional hypothesis, we're going to be using 2.101. Now we can finally calculate something. There's a problem. Our t distribution, our t formula can take on two forms. So we're going to write out the t formula for two independent samples t-tests. Cool. Here, I'm only going to give you one t formula for two independent samples t-tests because I'm under the impression that it holds either way, and the way that this is going to be written is we have t, and we're going to write in brackets, if you're following general APA formatting, the degrees of freedom. So what we do next is we follow that up with a particular formula. So what I need to do is figure out what goes in the numerator and then what goes in the denominator, and if there's any additions that need to go on. And I'll talk about additions in a second. So in our t formula, we're trying to test if there's a difference between two sample means in order to figure out if there's a difference in the population's means. So what are my sample means? Well, I have written in my null and alternative hypothesis treatment minus control. So that's what I'm going to do here. In the denominator, we're going to calculate something for our t-test that's known as the estimate of the standard deviation of the sampling distribution of the difference between sample means. You can stop watching now if that just terrifies you to no end, but honestly, You get used to it if you work at it a lot, and if you don't, it's 1 mark or so on an exam. So we're going to calculate something that looks like this. So let me write out what the heck this says. Estimate of the standard deviation of the sampling distribution of the difference between two sample means. If you don't think that's a nightmare to say, so does everybody else, because we call this the standard error of the difference between two sample means. Or if we really want to shorten it, we call it the standard error and hope everybody knows what we're talking about when we have two sample means. So that's what I'm going to shorten it to. If I say standard error, I'm referring to the denominator in the case of a 2 independent samples t-test. That's it. Or I'm talking about, if you really want to think it through, the estimate of the standard deviation of the sampling distribution of the difference between two sample means, and just recite that in a mirror 800 times and you'll get this good. Or recite it in front of tutorials 100 million times. So we have to calculate that lovely thing, and yes, I will write out the formula for that, but first I want to talk about additions. What are additions? Sometimes people want to know if the difference between their treatment and their control group is equal to a particular number, like 5. And so you would put 5 here. Maybe you're interested in knowing if the difference between your two populations is equal to a certain number. That's what we did with the 5. We tested to see if the difference between the treatment and the population control mean was equal to a particular number, and if you had these additions, you would specify them in your null and your alternate hypothesis, and you would know what you were doing ahead of time. Specify in HO or H1. And that's all. So if you haven't specified these in your null and your alternative hypothesis, or that you're still comparing the difference between your treatment and your control group to a number that is 0, you don't have to include these. So I'm going to, for most people, cross these out and say they must be specified in the null and alternative hypothesis. Not always necessary. Required. Cool. So what is this lovely, lovely standard error thing? Well, unfortunately, the standard error actually depends on whether you have homogeneity or heterogeneity of variance. So here we go again. Homogeneity versus heterogeneity. There is 0 reference to the color that I use and the thing that is happening in this case. By the way, I have no idea what I used for hetero and homogeneity before. So in the case of homogeneity of variance, let's cancel that side out, we're interested in calculating this thing called pooled variance as part of our standard error formula. And so the formula becomes, here's a nightmare. The square root of our pooled variance that has been multiplied, or is then multiplied, by 1 over the sample size in your first group plus 1 over the sample size in your second group. And that probably looks unhappy. You can reformat this to look like the pooled variance over the sample size of your first group plus the pooled variance of, over the sample size of your second group. So what is this pooled variance? This pooled variance essentially is where you have the same variance in both of your groups, and you might have different sample sizes in them. So you want to make sure that your variance is pooled a little bit like an average between two groups that have different sample size of them, in the favor of the one that has a larger sample size. Because when you have a larger sample size, you have a better estimate of the population parameter that you're trying to estimate, in this case the overall variance in the population. And so our pooled variance is going to be equal to the sums of squares in our first group plus the sums of squares in our second group divided by the sample size of our first group minus 1 plus the sample size of our second group minus 1, second group minus 1. And if you don't know, okay, SS in this case is simply going to mean sums of squared deviation scores. Scores. And yes, that's a very long name, which is why we shorten it to sums of squares, or SS1 and SS2. And so what do we do when we're trying to calculate our sums of squares if we happen to already know, for instance, a variance? Well, sums of squares is simply equal to our variance of perhaps whatever group you're interested in times your sample size minus 1 in the sample. So all I would have to do in order to make this for the sums of squares of my first group is add a 1, or if we're trying to deal with the sums of squares of our second group, you could add a 2. I'm sure that you can extrapolate from this. I'm not going to do that by hand, thanks. But all you have to do now is, once you've calculated your sums of squares 1 and your sums of squares 2, get your pooled variance through the formula and drop it into the formula above. And that, sorry about the scrolling, is how you get S x bar 1 minus x bar 2. Do not forget to do the square root. The number of times people forget to square root is insane, and you just end up with the wrong number if you have to do this by hand. So if you do have to do it by hand, I'm very sorry, because it's a pain. What if you have heterogeneity of variance and you need to calculate the standard error? Well, it's the same symbols when we're referring to the standard error. It's just we have to know that we're dealing with heterogeneity of variance, but that is equal to the variance in our first group divided by the sample size of our first group plus the variance in our second group divided by the sample size in our second group. Add those together and then square root and you're done. Isn't that one nice? Do not forget to square root. Again, it's a pain if you forget to do it. Why do we do it like this? Well, we already know that we have heterogeneity of variance, so why would we ever want to pool the variances when we believe that the variance in the two populations are different? We're already accounting for the fact that we're going to have our degrees of freedom adjusted, but this is further adjusting our denominator so that we end up making it harder for ourselves to, if one of our variances in particular is incredibly large, it makes it harder for us to reject the null hypothesis, because the way the math works is we're going to be dividing the difference between our two sample means, our effect, the effect that we might be interested in finding, over the number that comes out of one of these two formulas, and if that number is a big number, well, it's bad. Let me show you. I'm going to make up data. I am going to make up data for our homogeneity of variance version first. So I'm going to pretend that I have a variance in my first group of 5. I'm going to pretend that I have a variance in my second group of 5. And I'm going to say that I have a sample size in my first group of 10, because that's how many dogs that we had, and in my second group was also 10. And the sample mean in my first group was 400, and the sample mean in my second group was 700. Now, what colors did I use for treatment and control? I don't remember. So this is my treatment side. I'm guessing here, I'm hoping it's correct. I'm pretty sure I accidentally used the same color. This is my control side. And so if I wanted to calculate the formula here, what I would have to do is do both the top and the bottom part of the formula. So the top part of the formula is my first sample mean minus my second sample mean, and then my alternate hypothesis and my null hypothesis didn't say anything about any additions, so we're going to pretend they don't exist. I'm also going to be calculating a t value, a t observed, or an observed value on my t distribution for the particular difference between my two sample means, given our lovely variability in the denominator that I'm going to actually write out the full formula for that I'm going to use. So I take my pooled variance, 1 over n1 plus 1 over n2, and I'm going to start plugging numbers in. I know that my sample mean 1 is equal to 400. I know my sample mean 2 is equal to 700. I know that my sample size, I don't know what this number is for pooled variance, but I know that my sample size in my first group is 10, and that the sample size in my second group is 10. Now I just need to calculate pooled variance. And so when I calculate pooled variance, what I have to do is go figure out, okay, I'm going to take my, here's the full formula if you really want it written out. You're going to take your variance in your first group and multiply it by the sample size minus 1 of that first group, and then you're going to take the variance of your second group and you're going to multiply against the number of people in your second group minus 1, and then you're going to divide that by n1 minus 1 plus n2 minus 2. And you can see how formulas, when you start jumping them or lumping them in together, they can get pretty terrifying. So what do we need to do? Well, I need to start plugging numbers in so that I can get my pooled variance and plug that in here. Well, I had a variance of 5 in my first group. I had 10 dogs minus 1. I had a variance of 5 in my second group and 10 dogs minus 1. Hey, I only have to do the math once because I was really lucky in the numbers I chose. Then I have 10 dogs minus 1 in my first group plus 10 dogs minus 1 in my second group. So this basically sums down to, I'm going to do this in green. This sums down to 5 times 9 gets me 45. This sums down to, well, same thing, 5 times 9 is equal to 45. Not sure why I did the math together. When I add 45 plus 45, I'm going to get 90. So I'm dividing 90 by something. What's my denominator look like? This is equal to 9. This is equal to 10 minus 1 is equal to 9 for n minus 1. n minus 2 is also the same. I have 9 plus 9. That gets me 18. I'm dividing 90 by 18 to get my pooled variance. And my pooled variance is equal to 5. Probably could have guessed that, but I wanted to make sure. So my pooled variance, when I have exactly the same number for my first variance and my second variance, and when I have exactly the same number of people in my first group and my second group, is literally just, you know, take your first variance, add your second variance, and divide it by 2. So my pooled variance is equal to 5. That means that I get to scroll all the way back up and put 5 here and solve. So let's solve. I have 400 minus 700. That gets me negative 300. I have to square root at some point, but I'm going to take 5, divide, 5 over 10, and then go 5 over 10. That's how this works. You can do that sort of thing where you take, 5 divided by 10. 5 divided by 10 and get your number. And so that is going to get me 0.5 plus 0.5. That sums up to 1. Square root of 1 is 1. And I have negative 300 divided by 1 as my t-value. That just equals negative 300. Alright, I just took a pause right there to make sure that my math was actually correct, and it is. We in fact have a t observed with the degrees of freedom of 18 equal to negative 300. That is a very, very rare t-value if the null hypothesis is in fact true. So, we'll get into that in a second. Let's take a look up there and see what happens when we have heterogeneity of variance using pretty much the same numbers. I'm exclusively going to be keeping the same numbers. So we're going to take our treatment and our control under heterogeneity of variance now. And we're going to say, okay, treatment, we're going to change the variance in our, this is variance now. We're going to take the variance in our first group and we're going to say that is still 5, and we're going to take the, variance in our second group and we're going to say that one's equal to 30. If I do the heuristic of take my largest variance divided by my smallest variance, I'm going to get 30 divided by 30 divided by 5, which gets me 6. And that is larger than heuristic. That means we have heterogeneity of variance. Cool. We're still going to say that our sample size in our first group is 10, and our sample size in our second group is 10. And we're still going to say that the mean in our first group is 400, and the mean in our second group is 700. So what happens here? Well, the math just got a heck of a lot simpler, because our t with the degrees of freedom of unknown, because I didn't calculate the degrees of freedom here, I did end up putting the formula for that above if you want to give it a shot. Well, we're going to have 400 minus 700, and we're going to say that the denominator is equal to 5. Whoa, we're going to get rid of that. 5 divided by 10, because our variance in the first group is 5 over the sample size of 10. We're going to add that to 30 divided by 10, because 30 was the variance in our second group. Now all we have to do here is solve. We now have negative 300 divided by 0.5 plus, yeah, I should have been able to do that in my head, 3. And so we end up with, what's these combined, 3.5. We end up with a t-value of negative 85.714. 0.714, let me go get that last digit, 3. Cool. Well, not cool, annoying, because that's a heck of a lot of math. And so, what did we learn? We learned that when we calculate the t-statistic using heterogeneity of variance, we end up with a smaller number than if we calculate the t-statistic using homogeneity of variance, which I'm just going to circle in red here. T18 is equal to that. Keep in mind that I did change my values right here from standard deviation to variance, because I ended up screwing up the math there and using the variance, and well, using 5 as a variance instead of a standard deviation. So, sorry about that. No, I'm not editing it out. We all screw up sometimes. Honestly, screwing up by hand is a lot better, and figuring out where your mistakes are than clicking a whole bunch of buttons in SPSS, it telling you, hey, I'm done, and suddenly being told by peers perhaps that, hey, you've actually done your data analysis wrong in that paper you're trying to publish 2 years after you've forgotten how you did the data analysis. It's probably happened somewhere, and it's probably quite embarrassing. So I'm going to list a couple of things out because we've gone all over the place. I'm going to list out what our homogeneity degrees of freedom is. Degrees of freedom. Well, that was 18 because we were using the degrees of freedom total. We were using an alpha equal to 0.05 or 5% type 1 error rate. We ended up getting t critical values that depended on whether we had directional or non-directional hypothesis. So, if we had a non-directional, we had positive and negative 2.101. If we had directional, we had either a positive or a negative 1.7, and then I forgot the rest of the numbers. Let me go look. Where is my degrees of freedom? Rejoin here, perfect. At 1.734. For somebody that doesn't have a short-term memory, I'd consider most of that a win. .734, I nearly forgot what it was. So it's either positive or negative, but not both. So we also happen to get our t observed when we had homogeneity of variance versus heterogeneity of variance. And here's where I have to start splitting things up, because our t critical values we couldn't calculate because I didn't feel like calculating the degrees of freedom using the long formula. Maybe what I'll do is I'll paste it here at the end of this, and you'll be able to see it in this spot. I'm circling it so many times because I forgot what it was. Now, the last thing that we happened to get, and you might notice that I did, in fact, give you the values over on the right-hand side, we had gotten our t obtained, or our t observed, the number that we calculated from our raw data and didn't have any sort of population data in there, or critical values, or anything like that. And we calculated t observed of negative 300 when we had homogeneity of variance. When we had heterogeneity of variance, we calculated a t observed of negative 85.7143. Give me back my brush. 0.7143. What do we need to do now? We need to give that side more room, move it over so people can actually see it. But we need to figure out if we can support or fail to support our alternate hypothesis. Basically, we need to make a decision. So here is where we actually start to make a decision, and that's our final step. So, final step was step B, C, D, E, F, G, I think. I don't remember anymore. I'm as lost as, no, I'm not as lost as you are. I just don't remember what number we're on. Make decision. And if you've made it this far, you're doing great. And so what do we need in order to make our decision? We needed to draw our lovely t distribution under homogeneity on the left and under heterogeneity slightly flatter on the right. Cool. So we have a t with a degrees of freedom of 18. If we want to do this thing properly, it's averaged on 0, whereas over on the right-hand side for our heterogeneity of variance, we have a t of 11.919 with still centered on 0, just there's fewer centered people or scores that are centered around 0 and more that are sort of falling into the tails. Here's the difficult and annoying part, is if we decided to do homogeneity of variance, did we remember if we were doing a non-directional or directional hypothesis? Same with heterogeneity of variance. So I'm essentially going to focus on my homogeneity of variance, and then I will leave it to you to figure out how to make it work for the heterogeneity of variance thing, because it's super easy after this point. So let's take a look at what happens when we have a non-directional null and alternate hypothesis. Now I'm going to copy this so I don't have to do it later. Well, I have two critical values. Here's where approximately 1, 2, 3 are, negative 1, 2, 3. I had a positive and a negative 2.101 for my critical values. We calculated that our t observed was like, I'm going to draw it in green, negative 300, which is even more in the left direction. And we have to make the decision of whether we reject or fail to reject the null hypothesis, which is why I kept coloring in. Anything past this line is the reject region, anything above this line is the reject region, and anything between the two lines in pink is the fail to reject region, or the retain region. Either way, however it makes sense to you. And so with that negative 300, what do? I'd say we reject the null hypothesis and say that, hey, turns out that our dander shampoo actually does reduce the amount of dog hair that huskies shed, if you still remember that example that we were dealing with. Otherwise, scroll around a little bit and try to figure out what it was back in the beginning. So that's our decision. Please write it out in a full sentence. Because unfortunately people have lost marks on different assignments and different exams when they just say, I reject the null hypothesis. However, when you're writing a real research article, nobody just says, I reject the null hypothesis. They explain what it means, because nobody can remember what the research hypothesis was by the end of the results section, because they're too busy skipping the results section if they're undergraduate students. If they're graduate students, they're pouring through it, trying to figure out, is there a hole in this research paper? Can I make a hole in this research paper by digging at the stats? And they're lost. And the general saying is then profs don't have time to read. They have the grad students do that. But make sure that you spell out in very clear words what it means when you either reject the null hypothesis or you retain the null hypothesis, according to, hey, if we reject the null hypothesis, it turns out that our shampoo reduces the amount, or in this case for a non-directional test, changes the amount of dog hair that huskies shed. Whereas if I had retained the null hypothesis, I would say something like, my dog hair dander shampoo does not change the amount of dog hair a husky sheds. So that's pretty much it. Just make sure you write it out in a sentence. But what happens if I have a directional hypothesis and I say, I remember why I have that arrow there, I say that I looked in a specific direction. So let's look at those directional. My paint file is starting to be getting a mess, so oh well. Directional, and we have to know what direction we're interested in. And again, this is still for the homogeneity of variance, so we still have a t of 18. We have 1, 2, 3, 1, 2, 3 negatives, positives. And maybe I'm specifically interested in the alternate hypothesis that was dealing with a decrease in dog dander, which is a very good hypothesis to have in this case, because really we want to decrease the amount of dog hair that huskies shed because they shed an enormous amount. So we would say that our treatment in the alternate hypothesis minus our control, if we have a decrease in dog hair, then we should get a negative number. So our alternate hypothesis is looking for a number less than 0. Translate this into need negative number to reject your null hypothesis. Cool, so where would you put your critical value in this case? You would put it on the negative side, and in our case, our critical value is negative 1.734, I think. Negative 1.734. Cool. Anything below this line, negative 1.734, we're going to reject the null hypothesis. And anything up here, anything above negative 1.734, or even if it's a positive number, oh my goodness, we're just going to retain the null hypothesis. Doesn't matter if you have positive 300, it's a positive number. If I did my math correctly as treatment minus control in my T formula, then hey, I have to retain the null hypothesis. But I might want to check that out later in another research study where I control whether I collected data when they were during the winter shed or the summer shed. So if I reject the null hypothesis, maybe it's because I got a sample where we have a T statistic down here. Great, this is my reject the null hypothesis. But if instead I got a T statistic that was way up here, I would reject the null hypothesis. If I got another T statistic that is in the negatives, but not so far that it's more negative than negative 1.734, retain the null hypothesis. I'm going to let you figure out what happens if you have an alternate hypothesis of mu treatment minus mu control, where it's greater than 0. What kind of value are you expecting? You need what kind of number in order to reject the null hypothesis? Cool. And then maybe draw out the distribution and figure out what's up with that. Now, in terms of what we need to cover for an independent samples t-test, we are done. Like, done, including brain dead, done, probably on several people's ends, including my own. However, I took a look back through my video and realized I promised that I would, said that I would do something about the whole type 2 error situation. But if you aren't interested in effect size or power analyses, I'm only going to talk about them for like 5 minutes, but cut out now and go take a coffee or something. Or tea, or break, or nap, or homework. So, I'm actually going to zoom out and show you what we did. This is us. This is what I wrote. I don't know how long it took me at this point, but probably over 2 hours. And I'm not done yet. That's okay. Let's go talk about power and beta and how the two are related to each other. So let's head over here. So I mentioned something called power. We're actually going to start with the discussion of type 2 error. And so what is type 2 error again? It is when you make a false negative. And you said, oops, my thing doesn't exist. But the thing exists. In reality, you just had weird data and didn't find it, or you did something inappropriate when you collected your data and you didn't find it. Something happened. And so we like to talk about false negatives in both forms of a type 2 error, but also as the opposite of itself, called power. We don't like thinking about the probability of making a type 2 error. We want to think about the probability of making a correct decision if something's actually out there. So people call the opposite of type 2 error power, or the probability of correctly saying or identifying an effect when there actually is one, as opposed to incorrectly identifying an effect when there actually isn't one. That's a type 1 error. Scroll down a touch. Now, I keep writing these things like probability of correctly identifying an effect when there is one, because whenever you're dealing with probabilities like alpha and beta and power, you need to define the scenario in which you're talking about. The scenario being reality. Is the null hypothesis true or not? And that's what you need to say in every statement you make about alpha and type 2 error and type 1 error and beta and power. So what is power and why is power important? Well, we actually guesstimate power if we're interested in doing what's called a power analysis ahead of time, before we actually collect any data. And what does a power analysis do? Well, there's a few numbers that we need in order to plug into a power analysis, and a few concepts that need to be briefly talked about. There is something called effect size. You may have heard of it already. If not, what is effect size? You found an effect, or you said, hey, I found something. Hey, there is, can't spell, an effect in my data. That could be a difference between your two dog shampoos. That could be a correlation. What you need to do now is figure out what size is it. Is it small? Is it medium? Is it large? Is that effect small, medium, or large, based off of what you have in your data? And so you can basically calculate, hey, I have a small difference between dog shampoo, but a very, very, very large standard error, or a standard deviation, pardon me. Oh, no, you have only a small effect. If you have a really giant difference between your two sample means in this case, but a really, really tiny standard deviation in both of your groups, great, you have a large effect size. Basically, effect size is the observable difference between means in this case. So this is for the independent samples t-test. Is the observable difference between means close to or far from the amount of variability that's in the population? That's probably a little confusing, so just give me a second. Variability far from the amount of variability in populations. That's because when you calculate an effect size, all you're really doing is taking the difference between your sample, your treatment means, and your control mean. There we go. And you're dividing that over your pooled standard deviation. Not your pooled variance. You take your pooled variance and you square root it in order to get that number. So I'm going to move that because now it's in the way and incorrectly pointing at the wrong thing. So this here is known as effect size. I believe this one in specific is Cohen's D, but don't worry about that for the moment. Just know that if you are using a particular type of test, there is likely some sort of measure of effect for it. You just need to figure out what the formula is. So how do you figure out if it's small, medium, or large? If top is big and bottom is small, big effect. If top is small and bottom is big, small effect. Done. It doesn't matter if it's positive or negative. Could have a negative large effect size or a positive small effect size, whatever. The farther away from zero it is, the larger the effect size. Stuff you don't get if you just scroll through. Haha. So, how does this relate back to power? Well, it turns out that maybe if you're doing something completely new and you have no idea about whether your experiment on this dog shampoo versus regular dog shampoo, you don't know what the effect is going to be. So you say, hey, okay, I guess that there's going to be a small or a medium or large effect. How many people would I need, or how many dogs would I need to see a small effect? And a power analysis will tell you, given your effect size, given a whole bunch of other parameters, what you set alpha at, how many groups. In this case, we only have 2 groups, and they're independent. Are they dependent or independent? Are you doing a correlation? Are you doing a t-test? Given a whole bunch of these factors, it can tell you, hey, if you want to see a small effect that's only a 5-point difference, if it's actually there, you're going to need to use 444 participants per group. And then you go, I'm not going to be able to afford 444 huskies to take this shampoo home in my treatment group, and then another 444 huskies in my control group to take this home. Maybe I'm not interested in a small effect. Maybe I'm only interested in a large effect. And then you recalculate your power analysis and say, well, what if I have a large effect? How many people would I need in order to see a large effect if it is actually there? And maybe it tells you 42. And so, okay, you need to get 42 huskies per group, and if there is an effect, then you have a certain probability, your power level, of finding that effect, theoretically, if all of your assumptions are met. So power analyses, there are people who design programs. There's something called G-Power, G-star power, if you're interested in that kind of thing. So, power analyses. What do power analyses do? They take inputs and they tell you how many participants you're going to need, either per group or condition. It depends on exactly what you're looking for, in order to find some sort of effect. And that could be a small, a medium, or a large effect. Just, it depends on what you're looking for specifically. That is my rant on power analyses. Otherwise, I'm pretty much done. I'm going to zoom out and show you what I did. And then if you can, if you want to copy down anything, take a screenshot. It's actually too big for my monitor, so I can't zoom out anymore. Good luck. If you have any comments, if you want me to speed up or slow down or talk less about certain stuff, I'm probably not going to talk less about anything. But if you have an idea for another video, or if your class is going to be going through, dependent samples t-tests in the next 3 days, great. Let me know, and I will plop a video up for that one. Otherwise, thanks for being here, and good luck while you're learning.